Thanks for the organizers for inviting me. This is a joint work with Alessandro at Pompeu Fabra. So one way to think about motivating this project was to sort of take seriously this idea whether self-control type explanations can help us rationalize behavior that's otherwise sort of hard to reconcile with sort of standard models. And it's I'm thinking I have in mind mostly empirical work here based on initial theoretical work. And there's sort of two distinct literatures that sort of motivated what we were trying to do. There was one literature that was based mostly off of using large representative US data sets that was a little bit structural in nature. So there's one set of papers there. And then there's another literature that has become more popular recently in development that's also trying to get at the same idea. But the idea here is to offer certain kinds of interventions or certain kinds of contracts whose ex post take-up is then seen as evidence of one or the other kind of self-control problem. And one of the issues, I guess, that comes up with these literatures is that in general, the identification of time preferences isn't straightforward. We know, at least going back to Rust 94, that time discounting parameters in standard dynamic discrete choice models are not identified. So almost all of the empirical work that's been done on time inconsistency has been done within the context of the beta-delta model or the Strotz model of hyperbolic discounting. And the reason for it is fairly straightforward. With the addition of a single extra parameter, the beta, added to a standard intertemporal maximization problem, you capture at least what most people argue is one essence of thinking about time inconsistency, which is to draw a wedge between how you compare the present, which is, say, time period t here, relative to any other period in the future. That comparison is going to involve beta and delta, versus at the same point in time comparing t plus 1 versus, say, t plus 2, where that comparison is going to perforce only involve delta. And so the addition of a single parameter captured this notion of time inconsistency, and so this forms the main model within which most empirical work on time inconsistency is carried out. Now, if you go back to the Rust model, what Rust says is sort of the dynamic discrete version of this, even if you take away the beta, the delta isn't identified. And in this kind of approach, what we'd like to do is identify not just the delta, but also the beta as well. So the problem is a little bit harder than in standard discrete choice models. And then another thing that we'd like to allow for in our empirical model is allow for the fact that some people in a model, we'd like them to be time consistent, and perhaps some can be time inconsistent. So we'd like to allow for at least some basic kind of heterogeneity in the model as well. So that's another kind of complication that we wanted to consider. And then finally, another thing that's going to be useful when we're going to talk about identification here is going to be thinking about how this expectations operator or information about beliefs might help us think about behavior that people might think of as being non-standard. Okay, so how do we deal with this problem? So we deal with this problem by adding additional information to the model. So we add additional information in the form of elicited beliefs. So we're going to add additional beliefs to typical survey questions. We're going to combine this with survey responses to time preference questions. And then we're going to combine both of these with actual product offers, or these are going to be insecticide-treated nets, which are a health product. And we're going to use these three extra bits of information to identify preference parameters and estimate preference parameters in a dynamic choice model with time inconsistent preferences and unobserved types, where the unobserved types are going to be primarily characterized by differences in their time preferences. And we're going to estimate this model using data that we collected in an intervention that we ran in the state of Orissa in India. So just to sort of give you a preview of what we're going to do, we're going to end up point identifying the time preference parameters, both what I'm going to call the exponential parameter delta, as well as the hyperbolic parameter beta. And in addition, we will be able to identify utility functions that are going to be non-parametrically specified that will vary by time and type, of course, up to standard normalizations. We're going to then estimate this model using our data. And using the data, what we see, at least in this particular context, is that inconsistent agents are a rough majority of the population. About 60% of the population is what we estimate to be inconsistent. On the other hand, we have two different kinds of inconsistent agents, or what we call what are called the naive and the sophisticated agents. And the naive agents actually respond very, very similarly to the consistent agents, at least for the range of counterfactual simulations that we consider. And so about 90% of our sample indeed behaves as if it's consistent relative to the counterfactuals we consider, while about 10% of the sample are considerably more present biased than everyone else. We also allow for differences in other risk parameters and risk and costs. And these preference differences appear to be small, at least in terms of generating differences in counterfactual outcomes. Okay, so to just sort of give you an overview of the model, I'm going to present a very stripped down version of the model. So it's going to be a dynamic discrete choice model with finite horizons. The agent's going to take action in each of 3 periods. So in the first period, the agent is going to decide whether or not to purchase an ITN, and if so, which of 2 possible contracts to choose. So one of the contracts is going to be a standard contract or a loan contract to purchase an ITN, whereas the second kind of contract is designed to be similar to the kinds of contracts that are offered in typical experiments in development. They incorporate a sort of a commitment or a pay up front kind of design. And in the usual development RCT, the take-up of these contracts is seen as evidence of some kind of inconsistency. And one of the things we'll show with this paper is that mapping from take-up to saying something about preferences may not be warranted. In the time period 2, malaria status is going to be realized, and the agent is going to decide whether or not to retreat the net in order for the net to retain its effectiveness. So these nets need to be dipped in insecticide every 6 months in order for them to retain their effectiveness. And then finally, in period 3, the agent takes the action again, and that's when our intervention concludes. So we're going to use these agent choices as well as laws of evolution for the state variables and survey information in order to recover preferences. So that's sort of a rough overview of what we're going to do in the model. So let me give you a sort of overview of the different ways of the different types of agent in the model. So at the very least, we'd like to have time-consistent and inconsistent agents. And following the literature, we're also going to allow for 2 different kinds of inconsistency. We're going to allow for naive inconsistent agents as well as sophisticated inconsistent agents. So the primary ways in which these 2 types of inconsistent agents vary is with respect to the third bullet point here, which is how most of the literature has conceived of this. So sophisticated inconsistent agents are those who are aware of their time inconsistency and incorporate it into their decision-making procedure, whereas naive inconsistent agents are agents who, while they're inconsistent at period T, they think they're going to be consistent moving forward, and so therefore they don't incorporate their future inconsistency into their current plans. In addition, because we have additional information, we can also allow for these different types of agents to differ along two other dimensions. And the main reason to do this is to think about whether these differences in behavior are really coming from the awareness or the differing levels of awareness, or from other differences in parameters. So we're going to allow our agents to differ by the extent of the present bias. So of course, for consistent agents, the present bias there's going to be no present bias, so the beta is going to be equal to 1. But we're also going to allow the naive and the sophisticated agents to have different rates of present bias. So beta tau sub n is the present bias for the naive agents, and beta tau sub s is the present bias for sophisticated agents, and we're going to allow these to be different for the 2 types of agent. And then finally, we're also going to allow per period utility, the static payoff function in each period, to also differ by time as well as by type. So we're going to allow for agents to differ along all of these 3 dimensions relative to previous work, which typically only allowed them to differ by the third point. Okay. So to think about identification, what I wanted to do today was just give you sort of a rough idea of identification. And I'll proceed in 2 steps, which is similar to what we do in the paper. So we start by thinking about the case about identification when we think we're actually going to observe, when we actually observe types. So I'm going to call that the directly observed types case. And then we'll talk about identification in the case where types aren't observed, or what we might think of as the general case. And the reason to do it in 2 steps is in part because identification in the general case is going to build upon identification arguments for the directly observed types case. So I'll reduce the problem in the general case to the case where I can actually apply the results from the directly observed types case. So what I'll do first I'll show you some intuition to give you some idea of how identification is achieved when the person's type is a purely deterministic function of two observables. So the first observable is a set of responses to hypothetical time preference questions. So these time preference questions are designed to be very similar to the kinds of time preference questions that are asked in the usual sort of development RCT type surveys. And then also the response to this commitment product or a particular kind of contract that's designed again to be similar to the kind of contracts that are offered in these sort of situations. And next I'm going to show you identification when both of these are only roughly informative about agent type, and I'll show you what exactly I mean by roughly informative when we get to that part. Okay. So what's the key difference between what we do and a standard dynamic choice model? So the key difference really is an exclusion restriction, really. And in our particular case, we achieve it by collecting information about beliefs. So at some point in a standard dynamic choice model, you usually invoke a rational expectations type assumption that asserts that agents' beliefs about what's going to go on next period, conditional on this period, are equal to the observed transition probabilities in the data. So the key difference for us is going to be that we're going to elicit these transition beliefs for each household in the survey. So we're going to obtain household level variation in these beliefs, and that's what's going to be key to identification. So intuitively, what's going to happen is that these beliefs are going to lead to variations in the period t-value function while holding all of the state variables and the other elements of the period t-value function fixed. And that's really going to be the key behind one argument, the first argument in the identification step. So to just give you a brief overview of that, so this is just start by thinking about what happens in period 3. I have on the left-hand side this directly observed quantity, which is the probability that an agent of type tau takes action k, conditional on state variable xt, and what I'm going to call beliefs zt. So remember, this is the directly observed types case, so I observe the left-hand side directly. So first step, we directly can apply Hodson-Miller to recover the little g function, which is a function of the state variable. It has two components. The first component is just the normalized utility, and the second component is the forward-looking component of the utility function. The key really is that you have variation in beliefs conditional on xt. So the paper makes clear exactly what kind of variation you need. But intuitively, you can see here already that just variation in zt conditional on xt, as long as you have sufficient variation in zt conditional on xt, you can identify at least the two components separately, the say period 3 utility, as well as the product of the time preference parameters and period 4 and the continuation value in period 4. So in addition, once we impose some additional conditions. So typically we're going to we assume some commonality of preference parameters across types, and some additional conditions are going to help us separately identify then the exponential and the hyperbolic parameter for the different kinds of agents. One thing I should point out here is that we assume that the exponential parameter of the delta is the same across all agent types, whereas we allow for the hyperbolic parameter to vary across types. And that's a significant restriction. We are working on trying to think about models where we allow both the exponential as well as the hyperbolic parameter to differ across types, but so far we haven't quite been able to get full identification in that case. Another complication in this model is that, or another problem in this model is that we typically now in the literature there's a view for people, there's a view that agents aren't really completely naive or completely sophisticated, but instead they're sort of partially naive. So that's something else we can't really allow for within this model right now. We can test for full naivete or full sophistication, but we can't really allow for partial naivete. And the reason for that is that allowing for partial naivete involves adding an additional parameter into the model, and this additional parameter actually breaks how informative future choices are about earlier preferences, or how much earlier choices take into account future choices. And so for that reason, this is something again that we are trying to work on at this time, but we haven't quite gotten there as yet. So after having shown identification for this case where we directly observe types, we recognize firstly that part of the motivation for doing this paper was recognizing precisely that these time preference questions and the choice of these commitment products weren't necessarily good predictions about agent type, because they could be a function of all sorts of other things that are going on in agents' lives. And so we'd like to have a model that's weaker than the directly observed types case. And an added benefit of doing that is then we can actually test whether or not these standard mappings between these observables and agent types actually make sense or not, if we impose weaker conditions than we'd imposed previously. The problem, of course, is going to be now that identification is going to be much harder, since we can't use the standard kind of inversion arguments that we used earlier. So what we're going to do is we're going to break identification into a two-step argument using the key factor that really all you need is the type-specific choice probabilities in the second step. And once you have the type-specific choice probabilities, you can go back to essentially the directly observed types case and solve the model. And so what we do is we do an initial first step where we identify the type-specific choice probabilities, as well as the relative sizes of different types in the population. So what I'm going to call the pi sub t's. And this first step is going to be carried out by adapting the results from Kasahara and Shimotsu for, again, so if you think about the first step, really what the first step is, it says that the observed choice probability is a mixture over the different type-specific choice probabilities, and the weights of the mixtures are the pi's. And so we're going to use the Kasahara and Shimotsu approach to separately identify the weights, the individual components of the mixture, as well as the weights. So while it's true that we're not going to make exactly the same kind of strong assumptions about the mapping between these observables and agent type, we're still going to need some kind of a priori restrictions about the relationship between these observables and agent types. And so the weakest restriction that we've been able to come up with so far is that we should be able to order these ratios that I write down over here ex ante before we do the identification. So these ratios, you can think of this as sort of something like a monotone likelihood ratio, not quite. These are the fractions, so each of these ratios is the probability that an agent is of particular type 2 relative to some evaluated at two different points of R. So a set of sufficient conditions, for example, that would guarantee an ordering would be a set of sufficient conditions that I write down at the second set of slides. So for example, if we believe that time-inconsistent agents are more likely to purchase the commitment product, and sophisticated agents being the most likely, and similarly amongst those agents who report being consistent in the survey, they are the most likely to purchase the standard product, and naive agents more likely than the sophisticated agents, then that ordering is going to imply an ordering for the ratios. And that's going to allow us to carry through on the identification. But really all we need is an ordering of the ratios. And this is going to be important because when I show you the empirical results, we'll be able to test these two conditions, for example, and we'll be able to test more generally how accurately the deterministic type mapping is. So in addition to making these assumptions about information about types, we also need to make a set of assumptions that essentially tell you that once you condition on type, or once you know an agent's type, these variables are uninformative about choices. So conditional on state and agent type, these observables about time preferences need to be uninformative about agent choices, right? So this is reasonable if we think that the only information these variables are carrying is about agent type. It's unreasonable to the extent that you think that someone who makes these preference reversals in a survey is that these preference reversals are sort of reflective of some kind of defect in their decision-making process more generally. So if you believe that's the case, then these kind of assumptions are not going to be credible. And then finally, we require a relationship between the number of types we allow in the model as well as the richness of the state space. So in particular, right in this version, for the talk, I have only 3 types. So I'm going to require at least 2 points in the state space, and I'm going to impose a rank condition that says that I need at least as many points in the state space, and I need agents of different types to behave sufficiently differently at these 2 different points in the state space. So this is, again, reasonable to the extent that if types really behave similarly across the state space, it's going to be very different for us to actually separate out the different types. And then something that I think is also something that we've relaxed to some extent in the latest version, but not here. What we needed for some of the proofs was to require that all types exist with positive probability for at least 2 values of these observables R. So in the latest version of the paper, we are trying to relax this assumption. For special cases, it's somewhat easy to relax. But I think one can do it more generally. But for the proofs we have right now, we require all types to exist with some positive probability, which may not be great. Then finally, sort of finishing up identification and moving towards estimation, we're going to start with the Kasahara by implementing a version of the Kasahara and Shimotsu procedure. The big difference for us is going to be that the Kasahara and Shimotsu identification results typically relied on the length of the panel. So the usual identification argument sort of said, if T is as larger than 5, then these objects are identified. What we're going to use is the fact that the weights on the mixtures are going to be functions of some of our observables. So that's going to substitute to some extent for the length of the panel type arguments in the Kasa and Shimotsu paper. So that's the main difference in terms of the identification. Our implementation is going to be is going to follow fairly straightforwardly. We're going to first estimate sort of a joint distribution of actions and states conditional on other time invariant observables, and then we're going to implement we're going to implement lemma 5 in the paper, which essentially is an eigenvalue eigenvector decomposition. And so the eigenvalue and the eigenvector decomposition, subject to the ordering that we had imposed in the previous, I guess 2 slides ago, is going to identify for us both the different sizes of different kinds of different types in the population, the pies, as well as the type-specific choice probability, so the p sub taus. So these two are then going to be key when we go to the next step. In particular, in the next step, we're going to take these identified type-specific choice probabilities, and we're going to implement a minimum distance procedure that sort of minimizes the distance between these estimated type-specific choice probabilities and the model's predictions. So the first step is just is sort of an eigenvalue eigenvector decomposition subject to normalizations, and then the second step is taking these identified type-specific choice probabilities from the model and using a minimum distance approach. So we start with a given parameter vector for time preference parameters as well as risk and cost parameters alpha and kappa. We're going to compute these model choice probabilities starting from the last period, working backwards, construct the value functions, and then we're going to estimate theta by minimizing the distance between these model probabilities and the type-specific choice probabilities that we recovered from implementing Kasahara and Shimotsu in the first step. So that's as far as estimation is concerned. So what I'm going to show you, I just want to show you a couple of results. So the first thing I want to show you is the estimates for the population distribution of the different kinds of agents. So I have 2 different panels. We can look at the first panel first. So the pi sub c is the fraction of agents that are consistent. And R is, remember, the answer, and R is an indicator variable that's equal to 0 if you revealed yourself, if you were consistent strictly according to the survey, and 1 is, and R is equal to 1 if you revealed yourself to be inconsistent according to the survey. And we have estimates and their associated standard error confidence intervals. And so one way to read, say, the first panel is that consistent agents are about 40% of the population. And the first panel, about 60% of the agents are inconsistent, 50% of them are naive, and about 10% are sophisticated. The interesting thing is that these fractions don't change very much, irrespective of what survey response you look at, whether R is equal to 1 or R is equal to 0. So this is interesting because, remember, we didn't need to assume that, for example, pi c0 was bigger than pi c1 when we did our estimation exercise, right? And if you literally believe that the survey responses were very informative about time preferences, then the probability that you were consistent, given that you were inconsistent in the survey, should be equal to 0. But what we see here is that it's approximately the same as when you have R is equal to 0. Right? So this is one piece of evidence that suggests that these mappings from survey responses about time preference questions directly to time preferences may not be straightforward. And this is, it's consistent now also with the new literature in the lab, which suggests that these kind of time preference questions may not be only capturing time preferences, but really it might be reflecting a mixture of time preferences and marginal rates of substitution. So what we have over here is certainly consistent with that more general literature. So that's one set of results. Then I just want to show you one other set of results. So this is results for time preference parameters. So we have some issues with how we're doing the computation for the confidence intervals. We're still working on that. The point estimates suggest that the hyperbolic parameter for the inconsistent for the naive agents is pretty close to 1, whereas that for the sophisticated agents is about 0.57, whereas the exponential parameter is about 0.78. So the first point to note here is that the naive and the sophisticated agents have different rates of time preferences. And the second thing that actually is quite important is that it turns out that the sophisticated agents actually appear to be much more present biased than the naive agents. So now, this is not a model about learning or about agents learning about their type, but there is recent work in micro that thinks about agents learning about their time inconsistency, and certainly, these findings sort of are consistent with the idea that it's highly impatient agents who learn about or who know about their type and learn to cope with their inconsistency over time by becoming sophisticated. Okay, but that's not, this is not a paper about learning. So one of the things that we want to do here is sort of improve how we compute our confidence intervals. So far, we've implemented a minimum distance approach. We are at the moment implementing a maximum likelihood procedure to see if that improves matters. So just to sort of give you a brief summary of what we did in this paper so far, time inconsistency is often proposed as an explanation for observed choice behavior. But identifying time preferences is fairly difficult, especially with the conventional kinds of data that we collect, even when you have the freedom to collect your own data. What we tried to do in this project was to collect information on beliefs about the efficacy of insecticide-treated nets along with other information. We combined this with a field intervention. And we use these additional bits of information along with a lot of structure, namely a dynamic discrete choice model, with time separable utility and all of that. But the addition of this information along with this structure then allowed us actually to point identify the time preference parameters separately, in particular the exponential as well as the hyperbolic parameter. We were also able to allow for different types of agent in the population, which is again something that was something that we think is important in practice and not done in the previous literature. And the results seem to suggest that about 40% of the sample taken literally, if you take the pies literally, about 40% of the sample is time consistent and about 50% is naive. On the other hand, the naive agents are actually pretty close to consistent since their beta is approximately equal to 1. It's about 0.97. And in fact, I guess I thought I would be running out of time, so I didn't show you some of the counterfactual simulations we did. So we did a set of counterfactual simulations that tried to ask how different agents respond to changes in the price of the product. And we actually see that about 90% of the agents behave as if they're consistent, at least for the class of price variations that we study. About 90% of the agents behave as if they're consistent, whereas 10% of the agents do behave quite differently. And the reason for that in the counterfactual simulation really arises from the fact that the hyperbolic parameter for these sophisticated agents is quite different from 1. It's about 0.57. We also looked at differences in risk and cost preferences. Again, I didn't show you I didn't show you the estimates for this across different types, but there are differences in these risk and cost preferences across different types. But the difference in these, across types in these risk and cost preferences are actually relatively small, at least in terms of explaining the kinds of variation we see in response to say, price changes. Most of the differences in response to price changes seems to be driven by the time preferences, and in particular by the high rate of time preference for the sophisticated agent. So that's about all. We're hoping to extend this in several different directions, but that's where we are right now. Thanks.
The goals of the paper it had multiple goals. So one was to develop a model of the decision to purchase these insecticide-treated nets, and then about the decision to have the nets retreated over multiple time periods. The innovative aspect of the model was that it allowed for agents to be time inconsistent. It allowed for a lot of heterogeneity in terms of risk and cost, different risks and different costs and different preferences. A big part of the paper is devoted to demonstrating identification of the parameters under two different cases. One where the types are observed, and they use the responses to these survey questions about preferences over money delivered at different time periods to infer the different types. And then it also developed this two-step estimation approach. And then the last part of the paper, which I guess he didn't get to show you that much about, but which was applying the model to look at how differences in risk preferences, cost, degree of present bias, and awareness of future bias explain the variations in outcomes across people. Okay, so the model timing is in the first period, there's this decision whether to purchase a bed net, and the people are offered two different contracts. One is just with a commitment to pay for the retreatment, not pre-treatment, should be retreatment. And the other contract is one where they only pay for the bed net, and then they have the option later to pay for retreatment. In the second period, malaria status is revealed, and then households decide whether to retreat. Third period, again, it's kind of similar to the second period. They find out their malaria status, and households again make these retreatment decisions. And then fourth period is the end. Okay, and then one of the findings was that there are these different types of agents. 40% were found to be time consistent. 10% were time inconsistent but sophisticated, that they recognize their future time inconsistent selves when they solve their optimization problem. And then there were these naive sorts of agents that ignore present bias in their future selves, and they were found to be 50%. Okay, and so the type, sometimes type is inferred directly from the data, and then sometimes type is allowed to just be unobserved. Okay, so overall, I thought it was a very interesting and innovative paper in the way that it specified the structural model to study these decisions in its approach to identify model parameters. I mean, there are a couple other papers in the literature, but this paper extended those other papers by quite a bit. I liked very much that the authors also presented a Monte Carlo study to show the reliability of their estimation method before they applied it with the data. And then the way they implemented the model with the data from the intervention, and then they used the model to assess the effects of like changing prices of bed net and retreatment. Okay, so overall, I thought the identification arguments were pretty clearly presented, but it would have been useful to say more about what's parametrically identified and what's non-parametrically identified, because I mean, the only parametric assumption they really go through is the assumption on the error terms, but they never discuss, you know, whether this is necessary or not. Because I know this other paper by Fang and Wang, they use this conditional choice probability approach where you don't have to make parametric assumptions on the error terms. So I was wondering, you know, if possibly that could be relaxed here as well. Then in the paper, households, well, this paper is unique in using this expectation data where households had beliefs about different protective benefits of bed nets. But then I wondered, maybe the households, maybe it wasn't just their beliefs, maybe the households actually have differential exposure to mosquitoes. You know, maybe the households just live in different areas, and some people live near water where there's more mosquitoes. And I don't know if it matters whether these differences in beliefs actually reflect differences in technology or not. Because it seems that it would matter for solving the model, because when the household solves the optimization problem, they would use their beliefs. But then when you actually do simulations based on the model, it seems then you would actually use the true technology, you know. Beliefs seem to just be modeled as beliefs, but I wondered whether you could allow for differences in technology. And then over time, it seems the beliefs about malaria exposure go down. There seem to maybe be seasonality effects that are discussed in the paper, but that didn't seem to be incorporated into the model. The model allows for risk aversion with respect to consumption, but I thought maybe you could also allow with respect to health status. And then in the model, I don't think that malaria affects earnings capacity. You know, there doesn't seem to be any cost of having malaria other than this utility cost, but it could be that wealthier individuals would invest more in prevention because the cost to them of being sick is higher. And then in reality, of course, the model doesn't end after 4 periods. And normally people would specify a terminal value function. And so, but it wasn't done here in this paper. So I was just wondering why. And then this point came up, like why the model couldn't be estimated by simulated maximum likelihood. And then I wasn't sure exactly what weighting matrix was being used, whether a CCP approach is possible, or that's the conditional choice probability approach. With regard to the empirical implementation, the paper mentions that a lot of households already own bed nets before the intervention, and a lot of households were already sleeping under bed nets. So this would, since that's a decision in the model, this would be an initial conditions problem. And so normally you would have to make some additional assumptions, like that the initial condition is independent of the error term conditional on type. So it wasn't really explicitly discussed how you deal with the initial conditions problem. And then it would seem to me that owning a bed net might be a big determinant of purchasing decisions. I also wondered, if these households had bed nets, whether they had retreatment options on their own, whether there were, because it seems like there should have been some way for them to get the bed nets treated if they already owned them, outside of the intervention. And then there is this issue that the bed nets, there's certain sizes, I think, and then households that are really large, maybe not everybody can sleep under the bed net, and household size was the only thing incorporated in the model as a factor affecting the probability of getting malaria. But it seems like maybe you'd want to also incorporate information about the age of household members. Maybe if you had infants or older people, it's very dangerous for them to get malaria, so something about the actual demographics. It wasn't clear to me if households actually know their malaria status, because the models seem to assume that they did. And there seemed to be some effort to test them, but it looked like only a subsample were tested. So I wasn't sure whether the households were actually given information or whether it was easy for them to find out their own malaria status. And then the paper discusses how the bed nets are currently suboptimal, but it never really explained by what criteria. Maybe it's not optimal for 100% coverage. I think there should be some discussion about what would be the efficient level of coverage. And then in reality, malaria can be cured by taking medicine, I think. And I'm not sure if these households have access to medicine, or how expensive the medicine is, because an alternative to buying these bed nets would be to just get malaria and then just take medicine and cure it, so that part is not really discussed in the paper. But these were just some additional ideas for things you might be able to mention in the paper. Okay, I think those are all the main comments that I had.
All right, thank you.
Okay, all right, thank you.